All right, today we're going to go back to the Pythagorean theorem a bit and talk about it in terms of similar triangles and projections, and we'll get to that. But first I wanted to talk to you a bit about the golden rectangle and the golden ratio. So you'll see I have constructed here the assignment from set 3 from yesterday, but I've added a few more things to it. And there's this cool thing about the golden rectangle that you'll have noticed from constructing it if you paid attention, which is that the golden rectangle is a rectangle with a certain ratio between the sides that you found out, right? But the golden rectangle is also composed of a square and another golden rectangle, right? Which is to say that the ratio between these two sides is the same as the ratio between this and this. Right? The rectangle you added on is itself a golden rectangle, which is pretty cool. So you can keep going infinitely down, right? So I added another little square here, and you could add another little square there, and another little square there, and another little square there, and you just keep infinitely making smaller and smaller golden rectangles. You can also keep infinitely going up. I've added another big square down here, and we've made another golden rectangle with the same ratio between the side and this length as we have between this side and this length, and between this side and this length. Right? And so I just thought that was an interesting thing to point out. We do see this golden rectangle pop up a lot. A lot of the Pythagoreans and ancient Greeks thought it was beautiful, and also not only because it is pleasing to the eye, it's a good shape, but also because it is in this way sort of mathematically beautiful, that it is sort of contained within itself. That the way to make another one is to take out a perfect square, right? And then you can have another one, or to add a perfect square, and then you add another one, right? So it's sort of this thing that isn't perfect in itself. It's actually kind of irrational. If you did the work there to figure out the exact value of the ratio, it's an irrational number, right? It doesn't repeat, actually. What it does is it keeps going forever. So it's an irrational number tied to a perfect square. So something that is perfectly rational and exactly right, glued together with something that is irrational and that it contains itself. It contains the rational within the irrational and the irrational within the rational. So it's very good. It's this sort of beauty that you can get from mathematics. And it also gives us a very simple an elegant proportion, right? So the golden ratio is not so much a ratio as it is a proportion, because the ratio is AD over AF, right? That's technically the ratio. But AD over AF, I've just shown you, also equals AD, which is the same as GF, right, over BF. BF over AD, so equals BF over AD. And so we actually have here, you see that AD is the geometric mean between the length of the rectangle and the length of the part that is added onto the square. So the height of the rectangle is the geometric mean between the length and this, right? So that's just cool. That it's a very elegant, oops, I wrote, no, that's right. So it's just a very elegant thing that we have this geometric mean. I suppose I could write it more clearly if I did it the other way. BF over AD equals AD over AF. Where there's really only 3 terms in the proportion that describes how this rectangle is made. So there you go. There's the golden rectangle. That's why people think it's really cool. And it also, so again, if you keep making these squares, you get that same nautilus spiral out of it. it that we had earlier, right? If you you can kind of actually see this line here. If you extend this out so that it keeps going around the bigger and bigger squares, you get that same perfect spiral. So there you go. There's the golden rectangle. There's more to say about that, but we'll leave it there for now. Let's talk about projections, because there was some confusion about this earlier. And we're going to reprove the Pythagorean theorem using not areas, but projections. So the projection of a line onto another is the same as saying how much of this line does this line take up, right? So if I said the projection of BC onto AC, it would be how much of this line is taken up by the line BC. So it's the amount that it is over, kind of, if you look at it that way. Like if there was a light shining straight down from above, how would BC project onto AD? And so that would obviously, or onto AC, and that would obviously be DC. So DC is the projection of BC onto AC, right? And the same thing here. The projection of BA is AD. And the thing that we learned about projections is that the projection, the side is the geometric mean between its projection and the entire hypotenuse. In a right triangle, only talking about the legs. So with those limited circumstances, we can say that one leg is the geometric mean between its projection on the hypotenuse and the hypotenuse, right? So the altitude is going to divide this neatly where the projection is, because it's a straight line down from this point, so we can get our nice projection there. So the way we can write this is that if we label these sides, it might be a little easier to see how this proves the Pythagorean theorem. So we're going to label this A, B, and C as is sort of traditional. And then we'll give this one X and Y so that we can have these two. So X is the projection of A, Y is the projection of B, C is the entire hypotenuse. Right? So if you remember about our projections, we've said that X over A, that's an A, not a 9, equals A over C, right? It's the geometric mean. Good? And then we also have Y over B equals B over C, right? So you have both of those things. Well, we can multiply and we get A squared equals XC, and B squared equals YC, right? Well, what would A squared plus B squared be? A squared plus B squared would equal, well, A squared is this, so let's put that over there, XC, and then YC is B squared, so A squared plus B squared is XC plus YC, right? And again, XC is just X times C, YC is just Y times C. Don't let the variables confuse you. They're just standards for numbers, because we don't know. So it could be that Y is 3 and X is 2 and C is 5, right? And so that would be fine, but we're not going to do that right now. The point is, these are just two numbers that are multiplied together. And when you just stick letters together like that, that means you're multiplying them. So we have A squared plus B squared equals X times C plus Y times C. Well, we know from the distributive law of multiplication that X times C plus Y times C is the same as C times X plus Y, right? Well, X plus Y, if we look at our diagram up here, X and Y together make C. So X plus C, or X times C plus Y times C is the same as C times C, which equals C squared, right? So we have A squared plus B squared equals C squared. So once we've proved the corollary to Theorem 62, that the leg of a right triangle is the geometric mean between its projection on the hypotenuse and the hypotenuse, we can use that to very easily prove the Pythagorean theorem. So there you go. Just another way to come at that and to think about it. But remember, the projection is just this bit. Projection of B is just y. Okay? So there you go. Your assignment for today is numbers on page 296, or sorry, 396, not going backwards, through 399. We're going to say 398 actually. Numbers 1 through 14, 19 to 21, and 26 to 29. Alright, if you have questions about this, or about the golden ratio, or about right triangles, or Pythagorean theorem, feel free to call me on the Zoom meeting, and I would be delighted to talk to you about it. Thank you.